So now we want to put this all together and apply it. We're going to determine spontaneity using the second law. And we're going to do it with an example. Is the boiling of water spontaneous at 25 degrees Celsius? Now, you may look at this and already know the answer. Water does not boil spontaneously at 25 degrees Celsius. It boils spontaneously at 100 degrees Celsius. So this may seem kind of silly. Why are we going to figure this out using thermodynamics when we can just know? The point is, we want to be sure we know how to use the second law of thermodynamics and make sure we get an answer that is consistent with what we know should be true. We want to start, walk before we can run. Let's determine is the boiling of water spontaneous at 25 degrees Celsius using the second law of thermodynamics.
All right, so we want to know, is the boiling of water spontaneous? So this is going to be a yes or no question. So, if you're faced with something like this, you can just at least guess. Yes or no, you got a 50-50 shot. But what we really want to see is kind of like why. We want to give a justification why. And as discussed, boiling of water, whether or not spontaneous at 25 degrees Celsius, we can go ahead and answer that this is going to be no. Okay, we know right away that this is going to be no because you've seen water at 25 degrees Celsius. That's room temperature. It's not boiling. Water doesn't boil until 100 degrees Celsius. So we're going to use some of our fancy thermodynamics to make sure we can confirm that answer. We're expecting to get no as our answer. Let's prove it so that way, we can apply it to some other chemical reactions or other changes where we don't know the answer offhand, just based on our personal experiences. So if I want to know if the boiling of water is spontaneous, or really any process is spontaneous, we can calculate delta S of the universe. And the sign of this, if we had a value for delta S of the universe, if it was positive, then it's a spontaneous process. Delta S of the universe is negative, not a spontaneous process. So we can figure that out, which one it is, by basically computing the delta S of the universe, and that's going to be composed of the delta S of the reaction plus the delta S of the surroundings. So those two components. And so what we can do is we can calculate the value for those two components, which we've already seen in other examples, and combine those together to give us our answer. And in order to figure out those values, we can use our reference information. So boiling of water, that is H2O liquid becoming H2O gas. And so liquid to gas, we can see we have our reference information. We have all we need right here. We can do some computing. So the first one we're going to do is a delta S of the reaction. That is going to be equal to, we know it's always the sum over products of S naught minus the sum over reactants of S naught. And so the products term, we only have one there, so H2O gas, so it's going to be the S of H2O. You do want to be mindful that we do need to be aware of what the phase is, right? Because these are both water, so we do really want to be careful that in the chemical equation, what are the phases that we're looking at and finding them out, because we can see these entropies are different, enthalpies are different. Those, kind of reference values depend on the phase, as we would expect, especially for entropy. And so we really want to be sure that we're seeing that, we're looking up the correct reference value. So H2O gas is right there, 188.8 joules per mole Kelvin, minus 70.0 joules per mole Kelvin. That's going to be equal to 118.8 joules per mole Kelvin. Okay, so check off on this one. Got that one done. So now we want to look at delta S of the surroundings. And we know that delta S of the surroundings is going to be equal to negative delta H reaction divided by temperature. So we need to figure out delta H of the reaction, which again, we can do using our reference information that's tabulated. Delta H reaction is going to be, there's no division in it. Delta H reaction is the sum over products of delta H F naught minus the sum over reactants of delta H F naught. So in this case, that's going to be the gas. So I look up my gas value, negative 241.8 kilojoules per mole minus my liquid value, which is a negative 285.8. I'm going to warn you right now, this may seem, this right here is one of the most common arithmetic mistakes. Minus and negative, it's the same thing as positive. We want to make sure we catch both of those. There's always a negative that comes from this equation, and then the negative that comes from the piece of reference information. That's a negative enthalpy. So when we put those together, we get 44 kilojoules per mole, which is then that delta S, whoopsies, delta H of the, delta S of surroundings is 44 kilojoules per mole divided by the temperature. And there's a negative. Negative delta H, so negative 44 divided by 298 K. That is going to be equal to negative 0.148 kilojoules per mole Kelvin. So we were trying to calculate delta S universe. We had delta S of reaction. Delta S of surroundings are the two components. We can calculate each of those based off reference information, and then add them together. There should be a negative sign more clearly. It should be 298. That kind of looks like a 4. 298. Okay. A little bit sloppy. I'm trying to go too fast. All right. So we want to add those together now. Delta S of the universe is going to be delta S of the reaction plus delta S of the surroundings. Delta S of the reaction is 118.8 joules per mole Kelvin plus negative 0.148 kilojoules per mole Kelvin. So we really want to be careful here because you may be tempted just to add those numbers together. This is kilojoules and this is joules. And if you're adding values together, the units need to be the same. And this is very, very common of a unit conversion we need to be mindful of when we're doing thermodynamics to determine spontaneity. As the enthalpy values are in kilojoules per mole and the entropy values are in joules per mole Kelvin. So you generally end up with S reaction is in joules, S of surroundings is in kilojoules, and you need to account for those to get to the same one. Normally, we just go to joules because it's kind of the easiest. Or you can go to kilojoules, whatever. You can go to either one you want. I'm going to joules for both of mine. So this is 118.8 joules per mole Kelvin minus 148 joules per mole Kelvin. So with kilojoules, I'm just moving the decimal place 3 to the right, turn it into joules, or multiplying by 1,000, same thing. And so now that those are in the same unit, I can just combine them together, and I would get that delta S of the universe is equal to negative 29 joules per mole Kelvin. So what that tells us is that if this process were to happen at 25 degrees Celsius, if water were to boil, the change in the entropy of the universe would be negative 29 joules per mole Kelvin. That's a negative number. You're implying that the boiling of water at 25 degrees Celsius would lead to a decrease in the entropy of the universe, and that is impossible. What that means is that this process does not happen. This is not spontaneous. Water does not just start boiling at 25 degrees Celsius, which is consistent with our experiences. So we can use the second law of thermodynamics. We have confirmed what we already knew was true, which is good. It's good. We got the answer that we expected from the jump. No, not spontaneous is a no. So we were expecting a negative answer for delta S of the universe.
While we normally can't check does the sign of delta S universe make sense for this reaction because that's kind of where we're at, again, that's why we looked at water boiling at 25. We knew that this should not be spontaneous. And so we expected that this should be negative. That when if water were to boil at 25 degrees Celsius, that would be a decrease in the entropy of the universe. It does not happen. And so this is consistent. Water does not boil at 25 degrees Celsius, which is great. That's what we can use the second law to do. One of the primary advantages of using the second law is that we don't just understand is a reaction spontaneous, we can also break it down into this reaction and surroundings component and understand how those two things interact. So if we look at the delta S reaction, we had 118. That's positive. So we know that overall positive entropy things are favored. And so a liquid changing to a gas is favored. Water molecules not being in a liquid generally is something that would be favored from an entropy perspective of those molecules. But there's a cost to it. This is an endothermic process, and if those molecules were to go from liquid to gas, it would cool down the surroundings, right? It would cool down, say, in the case of the pot that you're in, and that would decrease the entropy of that pot, and that cost of decreasing the entropy by cooling down the surroundings is too great. Yes, you would get some benefit from, say, having the liquid go to be a gas. Those molecules would have a local increase in entropy, but the surroundings would have a larger decrease, and that doesn't happen when that is not okay when they combine together into the universe, change in entropy. But we can also start to understand what would make this spontaneous. We know that change in entropy of the surroundings is based all around heating or cooling. And we know that, heating or cooling, that change in entropy, that kind of the overall magnitude decreases when you go to higher temperature. Okay? So what that means is if you want, say, water to boil, you want this cost to decrease, which means you should increase the temperature. At higher temps, that entropy cost of cooling the surroundings doesn't matter as much because you don't change the entropy as much when you heat and cool stuff at high temperatures. That's why if water boils at a higher temperature. That's why everything boils at a higher temperature. And that's why that sort of guidance is always true, because the sign of delta S of the reaction for boiling is always positive, and the sign of delta S of the surroundings is always negative for boiling. Those are always going to be the case, and so you're always going to see, that's why it's always true, you increase the temperature to get something to boil. This sort of trade-off, the idea that there's an entropy change for the reaction that's, say, favored or unfavored, and the surroundings, the fact that they're in opposite directions, that's really common for a lot of chemical reactions. And there's kind of this balance that yes, the system would have a higher entropy, but the surroundings would be worse, or the surroundings would be better, but the system would be worse. Kind of those sorts of trade-offs are really common, and the fact that there's those trade-offs we're going to see are going to be useful for predicting how we can make something spontaneous. It's not spontaneous at 25 degrees Celsius, but at 100 degrees Celsius, water boiling is very spontaneous. So water, the kind of delta S of the universe, we expect it to be negative at 25 degrees Celsius. We expect it to be positive above the boiling point, right? And so that change in the sign of delta S of the universe tells us the spontaneity. It's going to change as the temperature changes. And so while the second law is the be-all end-all, delta S universe is what determines spontaneity. It's kind of a pain to calculate, and it's also really hard to think about. What does that even mean for the entropy of the universe to change? What we would prefer is a variable that only depends on the reaction you're looking at, right? That describes the reaction. Is this reaction spontaneous? Well, let's calculate this property of the reaction. So we're going to need one more thermodynamic variable.
All right. Another set of videos down. Participation 322 has 3 questions. So make sure you find all 3 of those, get them answered. That's due Tuesday. You got the midweek due Wednesday over on Chem 101. And then we will also meet on Wednesday for the acid-base titration lab. Kind of a blast from the past. Chapter 14 is coming back just a little bit. So we will do
we'll see that. Later in the week, we will have the second participation homework due this weekend, post-lab due Sunday, back to that kind of normal schedule. We saw pre-spring break, getting back into it for real. If you have any questions, let me know. Otherwise, answers for participation will go live Tuesday night, and I'll see you later this week. Bye-bye.